Hello. Hello, everybody. Hello, Damie fans. That's crazy. Damie fans. Sorry, I just gotta pull up one thing. This is not related to fluids, but my class keeps canceling my quizzes, and I feel like he's gonna make our final like 100% of our grade, even though it wasn't supposed to be. It's a little loud. Wait, let me turn that down. And I'm so nervous. We have our final next week. I don't know what our final's gonna be on. We've only done Moore's Circle. Like, I'm so scared. Like, he keeps saying everything is like extra credit, and I'm like, where's the credit? Where's the regular credit? Please, some regular credit would be good. But he also keeps like, it's so bad. It's so bad. Wait a second, let me see if anybody else wrote a rating for him. Let me see. Oh my god. Someone else wrote a rating for him. He's by far one of the most disorganized professors I've had. That's so funny. Wait, somebody gave him 1 star? Oh, I gave him 0 stars. Damn it, now he has a slightly higher ratio. Oh, he's so bad. It's so rough. My favorite thing. Oh wait, let me come on. My favorite thing about this guy was I asked him. I said, "Hey, so there's 4 lectures on indeterminate bending and loading conditions." I was like, "So, you know, like, when are we learning those?" He's like, "Oh, I teach it in 1 class," and I'm like, "Oh, so like, do we learn everything? Because I need to use it in strength and stiffness." And he's like, "I don't know. I don't watch the videos." And I'm like, dude. This guy is so bad. He's so bad. Anyway, let me stop coping. Stop being a hater. Fluids. Oh, here, wait. Let's pop over to this one. I started redoing this a little bit, so I think... So my issue last time was... Or I think one thing that I have trouble with, or was having trouble with Navier-Stokes in general, was the difference between VR and ZDR. Because in my mind, I was like, oh, we have like VR. Like, for example, like when you solve the continuity equation, generally what happens is you end up with like, you find something like this, where like VR or VY, for our other one that we did, is like a constant. And in my brain, I'm like, oh, like that's not right, because like there's velocity that's changing in that direction, but it's like that's not what it is. It's the change is in the R direction, so it's really DZDR. It's not VR, because D anything DR is 0. So that is, well, not D anything DR, because DZDR isn't 0, but VR is 0. So then when we go on to the actual, we'll write out the actual thing here. And that's the other thing that I'm pissed off about, is like the book doesn't... They're pretty decent about having like all the equations at the end, like in a more compact form, but they like just straight up don't have this one, and I don't know why. We're gonna check that out. Let me just see if they write it again after. I think I highlighted it somewhere. Nope. It looks like nope up here too. Oh wait, nope, that's continuity, and sorry, not continuity. Yeah, it's not here. They gotta be fluid dynamics. Exactly, fluid dynamics for sure. Z's. We're gonna finish up. So I have this problem that we gotta do, and then we're gonna do, I think, 1 more differential, but I think it's gonna be Bernoulli's equation if I had to guess, which is a little easier. Oh no, there's... Is it a frictionless incompressible flow? That sounds like Bernoulli's, yeah. Speed of the air relative to the wing and the absolute airspeed, that's fine. Ooh, interesting. That also is interesting. Oh wait, this one's easy too. Okay, and then I want to do some dimensional analysis because that is fun. Fun in quotes. It actually is pretty cool. Hopefully we can do. I'll try and pick one with similitude or similarity. Started yet? A little bit. We just did the conservation of mass, so I just got to grab my cylindrical coordinates so I don't copy them down wrong. We're gonna do Navier-Stokes right now. Sorry, let me just cycle through every single tab that's open. Okay, so it is... Hey Umbra, how's it going? By the way. My god, my tablet's... My tablet's just not... Sorry. Whoa. Alright. Alright, so we have row. Okay, let's actually do the header here. So this is the R component. This is going to be row times dvr dt. So that's 0. That's the steady. Plus vr. That's going to be 0. Navier-Stokes equation is not solved? Well, we're getting there. We're gonna have some stuff and then we're gonna integrate it. But because of the assumptions that we made, we're allowed to use Navier-Stokes. So this one, VR equals 0. And then V theta over R. So V theta is gonna be 0. We made the assumption that dd theta is not changing. We said it's symmetric. And then minus v theta squared over r. Now v theta... I guess we could have some v theta. Maybe. We'll have to think about it. I'm going to leave that one for there, though. dz. And this one is 0 because d dz equals 0. And then our other side... rho gr, which is just rg. Actually, so I cut this... Yeah, we'll just say g goes down. It's gonna be like a cone, so we could do it in any direction, but, you know, doesn't really matter. Minus dp dr. dpdr, that one's probably going to change, so we'll leave that. And then this is our shear stress. ddr 1 over r ddr vr. Well, that's 0 because our vr equals 0. Thank god. Plus 1/2. Oh, I'm running out of space. I don't know if I have space for that. D squared d theta squared. That's gonna be 0. Minus 2 over r squared. We're getting close. There's more d theta. Plus dvr over ddz equals 0. Okay, so let's see. We don't know anything about v theta. We don't know anything about p changing with respect to r. But we could do the other ones and see what we get. So we know about VR, and we know that VZ is going to be constant with respect to Z. I mean, everything is constant with respect to Z, but we don't really know anything about that value yet. In terms of boundary conditions, we do know that Z at R equals big R. I guess I should probably make like a... call that R. Yeah. at r equals big R, then our z is 0. Our bz is 0. And I think we can probably say v theta equals 0. I think let's say v theta equals 0. Because we don't have a rotating flow. I think it's gonna be that. So we'll end up with this. Because everything else cancels out, yeah. So then we have rho. It's gonna do the same thing for this. dv theta dt. Steady. Plus vr dv theta dr plus d theta over r, or I guess I can say dd theta equals 0. Is that what that is going to be? Minus, oh no, plus. Where am I? 3 terms, vr v theta over r, so that's vr equals 0. That's a lot of zeros. vz dv theta dz, that's 0. Hope everybody likes zeros. Okay, rho g theta, that's also 0. Is that 0? Yeah. Minus 1 over r. Okay, this one we can't say anything. dp d theta. I'm gonna leave that one for... wait, we said d theta equals 0. Plus mu. This is our ddr. 1 over r. ddr of r theta. Okay. rv theta. I said v theta equals 0. I'm just gonna circle that. If we end up with too much stuff, then maybe we don't do that, but I think we're gonna end up... Because I'm referencing like a... I'm not referencing it to cross stuff out, but the problem that I'm referencing is like they have a cylinder and there's another cylinder inside it, and they're asking about the velocity profile as it like rotates. So they're gonna have like v theta and stuff, and they're not gonna have... They're gonna have vr as well. But yeah, it would be... They would have v theta, but we have like, you know, fluid being pushed through a pipe, and so it's probably not gonna be rotating, but you know, we'll see if that if I get like 0 equals 0 equals 0 equals 0, then we goofed somewhere. E squared v theta over theta squared, that's 0 plus 2 over r squared. Okay. Theta plus d squared v theta over dz squared. What are we left with? Nothing. Okay, maybe not good. Maybe not good, but maybe it is good, because I mean, this is a linear momentum equation for conservation of linear momentum in different directions, and we said that our flow was going to be symmetric, so we should get 0 for our d theta, but it's probably a little more likely that that we would solve this for... We would end up having a v theta, and then Usually, like, everything cancels out but one thing. So... But let's do the z component and see. Also, let's see if I can kind of figure out the pattern here. There's going to be dvz dt, which goes away because it's steady, plus vr dvz over dr, plus d theta over r dvz d theta, plus vz, oh, I don't know at this point, let's see, vz, that's ddz, vr equals 0. Okay, still sort of promising, it's okay. Dude, if I have to do one of these problems in the final, I'm gonna be so borked. Okay, there's definitely a pressure difference in the z, because we're trying to solve for it, probably. Yeah, dp/dz, it's in there. And this is probably gonna be like, okay, we're probably gonna get two equations where we like combine them together, we end up adding them. So that v theta might actually come up. Okay. Plus mu 1 over r dr. I don't know why they put the r inside for every other one of them and then brought it out for that one. Strange stuff, man. R e z d r. Okay. dvzdr definitely changes. Like, definitely changes. So don't get rid of that. 1 over r squared d squared vc d theta squared. That one goes away, d theta equals 0. And then plus d squared. Really, only 3 terms? Okay, nice. D squared vz over dz squared, that goes 0. Okay, well, without doing anything else, let's just use the z one, I guess. I probably don't need to use all of them. I probably could have started with z. That would have been smart. Okay, so dp dz times 1 over mu equals, or let's say r over mu. And that r is just an r. But it will go into the, it's gonna be a little hairy. Okay, ddr r dvz over dr. Okay, so this is what we end up with. So I guess we need to integrate this? Yeah, maybe let's... how do I wanna... Because I want to get better at the notation side of this. I have a dr, but I have a dr there as well. But like the dp/dz, we're integrating with respect to r, so dp/dz is going to be a constant. So it's going to be r squared over 2 mu dp/dz equals r dvz dr. Maybe? And then r over 2 mu. I'm not doing any bounds. Wait, plus c. Ooh, and that's where we get the... we're getting there. We're getting there. Plus 1 over r. Ooh, except that's gonna be like a log. I don't know how I feel about that. That means we would get VZ equals the integral, well, probably just integrate it. R squared over 2 mu plus the integral of 1 over R is ln R dp dz. How close is that? Let's see, R squared over 4 mu. That is closer. And then the 1 minus R... Okay, that could be a... That I'm guessing is a plugging in thing. Let's see, so... We're kind of close. I think there's a limit. It's the bounds. Like, what are we integrating over? It's kind of goofing right now. I don't know if the R and the theta matter at all. I think it's only the Z direction that really matters. But I mean, it was good to do it out. Copium. It's good to do it out, guys, please. I swear. Ugh. Alright, let me... Okay. So R over mu ddr. You get R squared. You end up, it's good that we got an R squared there. I guess we're integrating from... Oh, this is gonna be a 4, sorry. Okay, so that's where we get the 4. That's good. Is it a negative? It is a negative, but I don't know if you just flipped it. Ln of 0 is 1. Or ln of 1 is 0. But... Wait a second. No, ln of 0 is... No, it's not. I lied. What am I talking about? I'm... Shh. Arithmetic. Okay. It's like close, but like not at all. Cause like, let me rewrite this. I don't like writing it like that. I want to write it like the proper separate way. Okay, so if we have this, I don't like writing it like this either. So dpdr equals mu over r times ddr. I'm gonna put it at the bottom. R dvz dr ddr. So then if we separate this, we get dp dz times r over mu times dr equals r, but that's the weird part, like rd, like it needs a, like it can't just be d. Like part of me wants to say like this and this, but that's like not how that notation works. I think I just don't like the notation. Cause like this is fine, but what is that D coming from? The D. it's like d of this. So really it's like r, it's like this. And then if we integrate this, okay, that makes a little more sense. Because then we integrate this with respect to r. So this will be, we're integrating it with, I guess I'm just gonna do an indefinite times 1 over mu times r squared over 2. And this one will be r dz, yeah, like this. And then this and this go away. So we get dp dz, but then this is, oh, that's fine, yeah. So dp dz times 1 over mu times r squared over 4 equals vz, sorry, plus c. And c is 1 over r. If you're integrating 1 over, am I integrating? I'm not integrating. Yeah, it's ln. Okay. And this is evaluated from, I don't know. Like, do I have to evaluate them both from that? Oh, also this is, okay, there's two things. I have to do some constants. So this is times c1 plus c2. So we need to have some boundary conditions, I guess, to fix it. Okay, yeah. Kidding. But the ln r is still so wacky. Why is it ln r? It shouldn't be ln r. Like, where's the, there's no ln r here. And like ln of the radius is not gonna be, okay. I don't like it. I don't like it, chat. Okay, well, what do we know about VZ? We know when r equals 0. Well, that's good. No, sorry. When r equals big R, VZ equals 0. Which means that dp... Wait, is that even gonna give us anything? No. Do we know V anywhere? No, we don't know V anywhere. What other conditions would we know? I mean, we know that it's 0 at the edge. That's the only thing we know. But clearly, it seems like they don't have any constant. Oh, do I have to use the shear? I might need to use the shear. Like saying like the shear at the middle is 0? Is the shear at the middle 0? I feel like it's maybe not. But that's sort of what we did on the other one, was saying like, okay, the shear at the middle is 0, and that's how we, because we do need two equations to solve for our unknowns. And it's either we do that or we do one of these other directions for velocity, and I don't think that's the play. Huh, very interesting. I don't know. You know what? Let's change gears. It's always good when you're stuck to just do something else. Let your brain unclog a little bit and come back. Let's maybe do this one actually. This is a writing one. Yeah. more of an explainy one. Maybe we can step through some stuff, figure some stuff out. See, this is what I got before. Oh, I assumed that, oh, dp dz equals 0? That can't be right, though. I mean, dz does equal 0, but I don't know. That seems like a scare. I guess it would be the same. Oh, fuck, I don't know. That's scary. Whoops. I guess we'll chew on that. Maybe it is 0. Although I feel like this, if it, oops, that's not what we were doing. This one. I feel like if it is this is a closer form to the answer that it is. Not that that's like the way that you should think about things all the time, but it's a good, like, it is a good direction. Wait, is this problem 5? Wait, what? Wait, are they named incorrectly? Oh, it's named 2 problem 5s, I see. I got a headache just by looking at what you scrolled through. It's okay. What? This? It's kind of like an ant walked all over the paper. Gotten some ink. It's okay. Look at this. This is like nice. Niceties. I'm gonna call this problem 6 because it's not problem 5. Can't lie about it. Okay. An example of a streamlined pattern for flow around an airplane wing is shown in the figure. Compressibility can be ignored as well as viscous effects. You can assume incompressible and an inviscid flow. Using this streamlined pattern, explain why the wing will experience a lift force. The lift force is the net surface force acting on the wing perpendicular to the direction of fluid motion. Very partial, it's super partial. So we're looking for why can we say there's forces here? Well, let's see. So we have incompressible and inviscid flow. There's only one other thing we would need to assume for Bernoulli's equation to be a thing, which is it has to be steady flow. And I think we can assume that. Let's start with that, just because I have a feeling we're going to trend towards Bernoulli's. There's streamlines involved, you know, that kind of stuff. Steady flow. Incomp, incomp, and in this. And yeah, we're trying to figure out. Let's see. So streamlines. Okay, forces are from changing momentum, i.e. Change in velocity. So that's our first kind of thing to prove, I think. Oh god, words? Oh, okay, math is bad, words are bad, come on. I hate exercises like this. No, this is great, this is like perfect. Okay, so we gotta prove that, like, there's a changing velocity. Because, I mean, we're literally, like, saying, like, just looking at streamlines, like, what does that even tell us? So, streamlines are perpendicular to the flow. Sorry, streamlines are tangent to the flow. Tange to flow. So, as they, change direction, like the flow changes direction. They're also so good for practice. I want to say, okay, wait, I don't want to say that. I want to say that I do want to say that they're tangent to the flow. I.e., no fluid crosses streamlines. No flow over. STLs. ST arms. So if we were to take like a control volume from here to here, So for CB1, const mass says m.1 equals m.2. And because A1 bigger than A2, and assumptions are there. Assumptions are assumption and properties. I don't know, and incompressible / inviscid. V2 doesn't equal, or V1 doesn't equal V2. So there must be a force. The forces / pressures present. Now the question is why is there a lift force? Tell me back when we learned physics and not English. Joke. I think it's funny because like physics and math are kind of like poetry when you actually like really understand them, and I kind of think that's beautiful because I think it's kind of awesome. It's kind of dope, but yeah, it can be frustrating. Like, I mean, especially like my math professor's like, guys, if you don't know how to do a problem, don't write me an English essay. Just like do the constants and stuff. But like in something like this, it's like, you know. So we have to say using this streamline pattern specifically. Explaining his poetry made it worse. Well, it's like, I don't know. Streamlines are such an ethereal concept. Like you can't, I mean, you can see them, but in certain flows only. You know? Seeing stuff that isn't there, that's art. So the lift force is the net surface of acting on the wing perpendicular. So why is there a force perpendicular, essentially? If there was a force normal, which is a drag force, that could slow the fluid down. But there has to be some reason why we can say specifically that there's a perpendicular force that's even acting. I mean, one thing I do know is that if you cut it in half, like, so we did a problem that was about like a wake. So there was a cylinder, and the cylinder sort of created this wake behind it, this velocity sort of profile. And if you cut it in half, you can find the lift, which is a cool thing to be able to do. But let's see. So drag tangent force. Oh, wait a second. But it's inviscid. Aha! There's no drag. There's no drag. So the drag tangent force normally would slow fluid. But this is inviscid. Inviscid flow. So there's no shear forces. Thus, force changing the velocity of the fluid must be normal and is a lift force. I was kind of like struggling. I was like, how am I gonna explain out the drag? And then it doesn't have any drag. That's pretty cool. That's pretty interesting. lift is such a crazy, like, lift and drag are just such crazy things that exist to me. It's like, if you like move something through something, like the air like wants to like go around and like push it up and like pull on it like back and stuff. I guess it makes sense because like if you think about being in water, then like you'd feel some forces that are kind of weird, but like happens in air too. What the heck? We live in that. Okay, anyway, let's do dimensional. Let's do dimensional analysis. Let's go back to math. Go back to just straight up hardcore math, pi groups, baby. Let's see. Okay, droplet impact. Three-body problem. Dude, what? He gave us a paper to look at the figures? That's funny. What kind of guy this professor is, though, for sure. Like, go look at this data and graph it against your pi groups, and then you'll see if you're right or not. Okay, King. Okay, consider a droplet of liquid impacting a solid surface. It's shown in the sequence of images. The droplet deforms and spreads out. If you are wondering why does anybody care about liquid droplets, take a moment to consider all potential instances in which liquids are atomized into droplets. It's thought that the maximum droplet, maximum diameter, let's do this. So Dmax is a function of the initial diameter, the impact velocity, the viscosity, the density, and the surface tension. Okay, we're gonna have to find units for surface tension. Use dimensional analysis to find the pi parameters that characterize the maximum droplet diameter. Are there any common ones? Well, it's probably gonna be... Let's just like guess. Let's just guess. So Reynolds number tends to be about... That's the dynamic pressure. So that's about like forces. Whereas I think the Mach number is more about... That's about like viscous effects, I want to say. And then the other one we might see is maybe like there's a surface tension one, like something called like the no, that would be like a capillary action. There's a capillary action one, and then there's another like surface tensiony kind of one that might show up. That's what I would guess. But let's go through. Okay, so we did this. We got Dmax as a function of stuff. Now we need to make our table, which is, let's see if I can do this right. So Dmax starts, and then Do, and then Uo, mu. I'm on. Actually, why don't I use my graph paper? And then rho, and then sigma. I'm gonna have to make a table in my handout for this for sure, so I don't have to like deal with all this. Mass, length, time, temperature. There's no temperature. I'm not gonna put temperature in here. We're only gonna mass, length, and time. It's a 3-space basis. Three linearly independent eigenvectors. Alright, so Dmax is a length, and D0 is length as well. And then this is a... I shouldn't really be doing it. Just be looking them up. And then mu is gonna be... this one is mass per length cubed. Sigma, I don't know, and then viscosity, I don't know off the top of my head, but that's why we have a reference sheet. Should I know the units of viscosity? Probably. Do I know the units of viscosity? Not off the top of my head. Whoops, sorry, gamers. I did it on the other dimensional analysis one, but let me check here first, and then we can double check to make sure it's right. Okay, it should be 1, 1, negative 1, negative 1. One, yeah, okay. Also, let's just, like, dimless groups. We'll start a little table here. So, density, viscosity, mass, time, or sorry, mass, length, time, temperature. Just the ones that I don't remember off the top of my head, you know. Well, density I can remember off the top of my head, but 1, negative 1, negative 1. For any weird ones, and like we'll put like sigma on here once we figure it out. Alright, so for surface tension, I do not know the units. Surface tension, sigma units. Sigma surface tension. Sigma maxing. The air liquid. Millinewtons per meter. Or newtons per meter. Millinewtons per meter. So newtons is a force. Ugh. Here, we'll put this on this. Sigma is newtons per meter. So that's kg meters per second squared per meter. So kg per second squared. Oh, I should do like pressure. So 1, 1, 1, negative 2. Force per area, so that's going to be kg per second squared meter. Pressure is a good one. We generally have to do pressures. That would be 1, negative 2, 1. Negative 1. Nice. I already forgot what it was. 1, 1, negative 2. And all these are 0, so that's fine. Alright, so now we have to find the rank. I'm gonna guess that this is the rank matrix here. Let's just get it over with, I guess. Rank analysis. I feel like whenever I hear the word rank, I think of the Hamlet soliloquy. His first one, where he's like, where things rank in nature, 'tis an unfettered garden that is left to feed, or whatever. And, I don't know, it's just a matrix. Okay, so 1, negative 1, negative 1, 0, negative 2, negative 3, 1, 1, 1. This is going to be negative 1 times 1 plus 3. And then negative 2, let's see, positive, negative, positive. Negative 2 times negative 3 plus 1 equals negative 4 plus 4? Fuck, that's not it. Man, where's my rank gonna be? Okay, let's see. 0, 1, negative 1, 1, 1, negative 1, negative 1, negative 3, 0. That feels like way too many negative 1s to be right, and 1s and negative 1s. We'll try it. Negative 1 times negative 3 minus 1. We'll do that too, just so I don't like goof it up. And then minus 1 times 0 minus 1. Okay, minus 1. That's a plus, so minus 2. Oh. I mean, we'll check it, but that should be good. Let's see if I got that right. Symbola, and Desmos, man, I don't know which. Pick your poison, really. Actually, my calculator's gonna be better at this, I think. I don't like a lot of matrix input calculators are kind of... Wait, but they just feel bad. That's my other calculator. My side calculator. I really need to get an in-between calculator that like works for the engineering certification, because you're not allowed a graphing calculator, but you're allowed a smarter dumb calculator, and I don't have one. And I could get one, but it makes me kind of feel a little wacky, you know? Okay, edit. I'm really hoping this is right. 0, 1, -1, 1, -1, -1, 1, -3, 0, and then mode, matrix, math, determinant, matrix, 4. Yes, 1. Let's go. Poggers. Okay, now we don't have to do anything. Well, it's not the end of the problem. We have to choose our repeaters. So grouping. So we have fluid properties. Fluid properties, flow, field, geometry, and energy transfer, which we don't have any. So let's see, DO is a geometry thing, I guess, kind of. And Dmax is also that. Wait, but we don't group that. Flow field is U. Viscosity and density. Oh, that's a good... And surface tension, I guess, is that? I guess we choose... Okay. So this is going to determine whether we have a inertial driven field or not. And so if we want to say that viscous effects are more important, then we have mu, which I feel like is not the case, because it's not really about the viscosity. It's more about the surface tension. I feel like, but the density of the fluid, I think, still matters more because it's falling and it has all this momentum. It's that pull between the inertia and the... So I'm going to choose that. Those are our 3 repeaters then. And then we do the pi groups. So we have rho, mu o, do, dmax is going to be, when we look at this, we say, did I ever do this with a matrix? Did we talk about doing that? So we did rho, VO, and DO, right? Yeah, I think I might have talked about doing this as a matrix. Because we can plunk it in and then have a, if I negate it, right? Let's try it. Let's try it. Well, I mean, maybe it's worse to do this way. Actually, I lied. Let's not do this way. Yeah, let's do this way. So like rho times A, or like A rho equals 0. So rho equals 0. Which makes sense because it's the only one of those that has mass in it, so it can't be there. And then length. So DO, okay, it's gonna be, how am I gonna assign these? How did I write them? Of I wrote them like that, that's not useful. Should write them the same order that the thing is in. So we have, I guess, A D max. Wait, no, I don't need to do that. I just need to say A. A plus B plus C minus 3D. We're getting there. We're slowly practicing. Plus 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 minus, yeah. A plus B plus C equals 0. And then time, we get negative C equals 0. But then A and B are still... Why do I not have enough equations? Hello? Hello? Oh, there's no A. Sorry. A is 1. Lol. So then B equals -1. Wait, so everything else is 0 and B is just -1? So our pi group is D max over DO? That's funny. I mean, maybe, I guess. Like, you're not gonna have any time. You can't have any time because nothing will cancel the time. And you can't have any mass because nothing will cancel the mass. So it's like a relative... Well, that makes sense, because, like, the bigger the droplet gets, the bigger its Dmax should get. And so you can kind of group those two together. That's kind of funny, though. Let me see. Okay. Let's do the next one. That'd be mu. Okay, so for our mu, so it's gonna be like 1 plus, I don't know, maybe it's not 1. In the mass, yeah, it's 1, well, yeah, 1 plus 1. Sorry, 1 plus D equals 0. D equals -1. And then our length, we have -1 plus A plus B. Oh, I didn't call it A, sorry. B plus C minus 3D. So then B plus C equals 1. And then time, we get -1 plus minus C equals 0. C equals -1. B equals 2. Yeah? Please tell me that's Reynolds number. It might be Reynolds number. I don't know. It kind of sounds like it might be Reynolds number. So this is going to be D max. No. It's going to be mu. Mu over... Let's see... Density? No. DO... Okay, let's just do this. B, C, D. So DO, UO, P, rho. So DO squared, UO. Interesting. And then DO squared, UO, what was the last one? And then viscosity? That's weird. I feel like that's not right. Did the units cancel out? What's viscosity? Oh, I don't want to do this in my head. Let me just solve the matrix and see if I got it right. I just have to set up the extra column as... it's okay, I got you guys. 3, 4? No, 4, 3. No. 3, 4. Yeah, 0, 1, 0. And then 0, 1, negative 1. And then we flip. Oh my god, I already had it flipped. That's so funny. Negative 1, negative 1, negative 1. That makes more sense. Why do I not have that when I did it? Why am I bad? Wait, also, why did I... Wait a second, I'm goofy. Wait a second. It should be like this. It should be this and then this, which is the Reynolds number. We're getting there. And then it'll end up being DO squared. But wait, no, negative 1. Wait, negative 1? Wait, Reynolds number. Yeah, okay, it's not squared, I lied. But why is that, like, wrong? What's up? Oh, no. I feel like the easiest way to do this would be to... I'll try it for this one. I think the easiest way to do it would be like... write the matrix like this. Right here. So this is B of 0, 1, 0. And then C of 0, 1, negative 1, and then D. Just so I can like reference it in the correct order, and then I won't ever get it wrong. Yeah, because D... and then... mu is 1, negative 1, negative 1. So 1, negative 1, that becomes a positive 1. Wait, should C be... No, yeah, C is negative 1. And so... Oh, D is negative 1, not 0. Hi, how's it going? Oh my gosh. I'm so glad I could make it to your stream for a little bit earlier. It was fun. Let's see, D is negative 1, so that would be negative 3 plus 1 plus 1 equals B equals negative 1. Okay, we're chilling. Reynolds number. We love it. I mean, it's the flipped Reynolds number, but don't worry about that. It's the same thing. Same difference. Dropping in to say hi. Aw. Hi, how's it going? I'm unable to add numbers together. Normally that is what we do here. Okay, all I need to do is this. I just need to say D. Wait, what was sigma? I don't remember. 1, 1, negative 2. It was good to see you. Aw, thank you. I liked hearing you talk about that stuff. It's funny because when I did it, we had to do Gaussian distributions and all that, but like we had like, oh, here's an average nominal value and there's an uncertainty on it. Like what is the, like what are the two ends of that? And then also like if you have a run of like 500, you know, values or whatever, like find like, you know, the standard deviation and find like the uncertainty to like a degree that you can say that like the deviation is on. So if you are trying to say like a resistor is like 50 ohms, like nominal, like plus or minus, you know, 0.5, like, you know, this with, you know, 98%, you know, confidence or whatever, or 90, was it like 99.5% confidence or something? I don't remember. But yeah, that's what we did in my stats. Or it was like, oh, you have a, you know, the two possible, like, you know, one mean could be here, but you know another mean could be here. And so then like, what's your actual mean and stuff like that. Very single, whatchamacallit, like single variable statistics, but it's kind of like single variable, but also like it's just a different way of looking at it, which is cool. Okay, so 1 plus b plus c minus 3d. Minus 3d is plus 3. And then time minus c equals minus 2 minus c equals 0. C equals 2. So then b. What? Minus 5? What the what? That's not right. I did something wrong. C equals minus 2? B equals 4. Minus 4. Plus 2. Okay, yeah, that's fine. This will be capillary action over oh my gosh, hi Cosmo, how's it going? I'm doing some dimensional analysis. What is that? Density? No. Yes. Density, what was B? I forgot what B was. D0? Oh. I just wrote C. It's not C. Okay, C. I don't remember. It's mu O. This is almost dynamic pressure. It's not though. It's something. I don't know what that one is. I love your stream titles because I never know what they mean, but they're still so funny. Oh my gosh, yes! Thank you for liking my stream titles. I always like go live. It's literally, bro, is incompressible. The joke there is that you can't use Bernoulli's equation on an incompressible fluid. Or non-incompressible. Wait, did I write I'm incompressible? No, I wrote I'm incompressible. Fuck, my joke. Oh no, I got it wrong. Yeah, I meant to write I'm compressible. Oh guys, I sinned for so long. Bro, it's compressible. Oh no, the wizard battle would kill me. I believe in your joke forever till the end. Thank you, Cosmo. It's okay, I would get killed by the wizard. He would Bernoulli me. What the fuck did I do? D-max over D0 equals function of mu over rho UODO Reynolds RE. And then whatever the hell this thing is. I don't know what this is. I'm its biggest hater. No, I don't know. It's like probably capillary something. Evil compression hex, go! Oh shit. Gets compressed. Wait. Fuck it, no. No, wait, how do I... It gets compressed. Oh my god, wait, the compression X. No, come back. Wait, what? No, that was so scary. There we go. I got compressed. It's okay. I'm compressible. Still the same mass, baby. Oh, goodness gracious. You compressed my background, too. Look, now you can see all of your guys' awesome comments all the time. Thank God you're compressible. I don't like this one. I don't like this one. This one's bad. See, the issue is they're all bad. This one is also bad. You'd be dead otherwise. Yeah, I would be dead. I would be so dead on the floor. I really like how Rev is talking about Fall Guys in Clem's server. Wait, am I lying? No, yes. They... Wait. No, they were talking about Fall Guys. Scary. True, I am scary. This is really unfortunate. I don't know why. Maybe I just can't integrate. But see, the issue is, like, if I put this into a calculator, like, Desmos is gonna get really mad at me. Actually, maybe it won't. Wait, let's go to Desmos. Oh, you know what I'm so sad about is that Hypnospace creation page. What? I'm not squished here? I'm squished here. That's so silly. That Hypnospace page builder doesn't work, and I found I used the Wayback Machine and it didn't let me download it, and I'm so sad about that. I think they should give me the files so I can build my own Hypnospace page after Chowderman eviscerated my brain cells. Okay, I'm just gonna call dpdzp, and then that's gonna equal u over r. P is also gonna be variable. Beautiful decompression X, go! And then this is times r. I'm trying to think about how to do this, like, not stupid. Oh, it's not gonna like this, is the issue. It is not gonna enjoy this. Boundless. Can you integrate for over R, or does it have to be X? Because I can change R to X. I can do that, actually. What is it gonna yell at me for? Integrals must have upper and lower bounds. The poor fucking Chowderman. Dude, Chowderman, get out of here. If you're Chowderman, I can't. Big R equals 3. What is it gonna yell at me now for? What do you want to take the derivative of? All of this, please. Wait, oh, is it not in the integral? Maybe I need to do X. Maybe it's not happy about me for not doing X. Oh wait, R is a value. Wait, why is it saying that? Why is it saying that? What? The answer is 6? I hope the answer is 6. Wait, what is the issue? I'm actually... Is it this? What? What if... Wait, what? Okay, fine. Here, I'll go 0 to 6. What do we have? U over... over X. But see, the issue is it's U over X. And then I'm just gonna put a placeholder thing, like E. This is a question for Symbolab, not for Desmos. Sorry, it's actually 2. Yeah, it's okay, you got it, don't worry. We'll do 0 to 2. It doesn't really matter actually right now, but it's fine. 0 to 2 is great. I don't know how I deleted the upper bound. Okay. Well, okay. I don't know what it's doing. It's scaring me. Come back upper bound. Now that one doesn't have any bounds. Oh my god. Okay, 0 to 2. We need u over x. U over x, and then we do x. Oh, but it's like stuck in there. I love number. I love number 2. I don't know. I'm like, guys, I'm like failing like my how can I integrate this thing? What if I just call it A for now and then D dx? Oh my god, that looks awful. Well, I don't know. That's also not really right. Oh wait, I just realized I was sharing that. Wait, I need to put on new music. What should I put on? I'm gonna put on... I asked and I immediately was like, no, I'm gonna put on something else. I'm gonna put on... I don't know, what's fun? What's a fun soundtrack? Because I could do Splatoon. This is kind of a Splatoon. Hey, it's Fluid Mechanics. Splatoon is very much the appropriate music. It's a banger. Okay, I don't know how to check this actually. I'm just silly, I think. Oh, sorry. Maybe I can check it on integral calculator? But like, I'm dummy. My brain don't work too good. Works pretty well, but not right now. Bro, why? Give me your secrets. Give me your secrets. Let me in. I don't know why it's giving me natural logs. Or maybe it's supposed to be giving me natural logs, and I'm not seeing it. Okay, let's think. If I get 1, natural log of 1 would be... That's gonna be hard to get. And the r over r squared is weird too. But that could be natural logs minus the stuff in them. But then you would have to get like a... I don't know. I don't know if this is the right path. I don't know if I've taken the right path, gamers. I'm gonna get rid of this stuff. We have not touched anything but the z direction, and this stuff is kind of freaking me out. So we're gonna politely move it along. Okay, there we go. Okay, now I can breathe again. Let's take a look. Maybe I like canceled something out that I shouldn't have canceled out. So the DDT is definitely steady. We like that. I think, okay, maybe it's also I just don't know what the 1 over r, like I don't know the order of that term that we're supposed to differentiate it in. Okay, but VR is definitely 0, so we don't have to worry about that. dd theta is definitely 0, so we don't have to worry about that. ddz is definitely 0, so we don't have to worry about that. There's no gravity, although that wouldn't make anything better if there was gravity in that direction. dpdz is fine, we can leave that, we know it's going to be there. Mu is fine. dvz dr is fine, that should change. And then d theta and dz don't change. So we end up with this. And and I don't know where to go, but that is fine. We'll just stumble around a little bit. Well, okay, so what are we trying to solve for? We're trying to solve for dvz. And this is a little dude who's stuck on our integral. So what if I just integrated it, like, straight up? I could do that. So that would be dp dz dr equals mu over r times r dv z dr. There's a d in there somewhere. I don't know about that one. Like, there's just a d here, and I feel like that's like, I feel like I gotta like do something with that. You know? Like, that's like not... I mean, I could put it over there, but that's not right. It's not, we're not differentiating with respect to mu. That's the other weird thing about this. Let's maybe look at the book. Maybe they have a version of them doing this beautiful... No, see, they don't have this term in theirs. They do have this term though, so we can see what they do with this, which is very, very, very similar to what we have. Because they have that like dr. Okay, let's see. What do they do with that? Equation B1. Okay, that's not what we're doing. What? Wait, sorry. Maybe they just skipped it? When does the theta component get used? The continuity reduces that, that's fine. Okay, B3, here we go. Rho, and so 0 equals DDR. And the other one reduces to the rho, yeah, rho PR. Sorry, I'm just looking, such a banger. Okay, yeah, so they have this term. Can I highlight it? Can I circle it? Let me circle it. It's really hard to see. This one and this one are what they have. And then on this one, we just have this one. It'd be faster to write all the stuff they don't cancel out, really. So since dd theta equals 0 and ddz equals 0, then by assumptions 3 and 4, v theta is a function of radius only. And dr, so they're saying this equals 0. That's crazy. But where are they getting the... Oh god, okay, v theta is ours like that? I feel like it's not. Vz is a function of radius. But they're differentiating... Oh, wait. Wait a second. Wait a second. DDR. Oh, I see. They just changed it from partials. Who cares? No one cares if you changed it from partials. I don't, sorry. That was mean. But so they have it equals 0. So they just have their DDR and then they get rid of it. So I guess they are just using the D notation as like, this is our way of getting rid of something. Like sorry, that's a weird way of saying it. When we integrate it, generally like you don't have to separate it, I guess, with the way they're thinking about it. So let's try that then. So what they're then saying is we can just integrate this directly without separating it at all or doing anything to it at all. DDR. Dance Dance Revolution. Exactly. That's me. I'm like stepping on the well, you know that video of Mo from The Simpsons where he's like, I'm gonna show you the self-defense. He's like, I'm gonna break it down for you, and then he like just starts dancing, and they all like, that's what I'm doing when I'm taking these derivatives. So we have dp/dz. Sorry, I'm getting lazy on my partials. True. That'd be a great damie vid. Well, but now I have a log. Now I have a log right there. When they get rid of the thing, they keep their 1/r inside there. Oh shit, did we keep our 1/r inside there or not? They took theirs out! They took theirs out! What are they doing? They took it, why did they take it out? Why can't I put it in here? Oh, probably because of like, okay, putting it in here wouldn't be the same thing. Sorry, that was mean. What if I take this out? What if I get them? What if I take this out and I integrate this first and then I say, oh, you know what? We could do that. What if I did that? That would be kind of silly, goofy of me. We say you are. You know, okay, it's actually not the worst thing. Because really what we're saying is that, okay, can I do this? Maybe? This would be r squared over 2. And this is gonna get, if we do r squared over 2, vz plus c ddr. No, we're still gonna get a log, god damn it, because of the c. I can't escape the log. I want to get rid of the log so badly. Why is there a log? Okay, does Navier... I'm gonna look it up. Should Navier-Stokes have a log in it? No, I don't think so. They're hating on it. This is a fluids class, not a forest class. There shouldn't be logs in here. That's a really bad joke. I started saying it and I was like, I can't keep saying this joke, and then I did say it and I was like, well, okay. Okay, TP times R equals, fine, I'll just have the thing in here. Mu. Hey Damie, how is fluids? Is it over? No, I still got what is it, 2 weeks? And then it's over. Fluids is great though. I do really like fluids. I mean, I just don't know why I'm getting a log in this equation, but fluids are never. Is it hard? I don't think it's that hard. Fuck, I have to integrate a log? There's no way. There's no way. Okay, I'm separating this. Never mind. We're going back to the good old days of I don't have to do any logs that early. Oh, it's over. I see. No, it's not that bad. This is just like, I mean, I don't know, you can take a look and see if you think this is bad. That's a lot of partial differential equations. It is a lot of partial differential equations, but it's okay. It's okay. And none of these I used. I just wrote them all out for fun, I guess. No, I thought I would use them and then I didn't use them. It's like everything turns into zeros, but you just have to like turn them into zeros. So it's not as bad as it looks. It does look pretty bad though, I will say. Everything is partial because everything is multivariable. Easy. Yeah. It's really not too bad. Like, I think the first part of the class is harder, or I think it's a lot harder, at least when I was taking it, because it's hard to get into the mindset of like thinking about assumptions and also just like learning about fluid properties and sort of like gaining some intuition for stuff. But after that, then it's not too bad if you're just like diligent. It really is just a lot of diligence. Like, at least this first part of thermo is kind of just a lot of bookkeeping. Like, it's a lot of math. It's a lot of keeping track of stuff. And if you you just have to know what you're talking about, though. Like, and I have a professor who's very, very particular, and people are like, oh, he's so hard. And it's like, well, I mean, he's particular for a reason. For my material and energy balance cast, my professor gave us a fluids problem. Oh yeah, yeah. Well, and any gas problem is also a fluids problem. So I'm taking thermo next quarter. It's at night. It's from 6 to 7 p.m. 3 days a week. I'm gonna die. I'm so sad. I mean, I think it's gonna be really easy. Okay, that's a crazy thing to say. I think taking fluids makes it a lot easier to do thermo, because I mean, a lot of what I've heard is like it's just Reynolds transport theorem and stuff like that. Thermo, transport, and quantum. Wait, is quantum the same class? That's crazy. I'm taking intermediate dynamics. I just had registration today and it did not go well, but we don't talk about that. Wait, oh, these are all multiplied together. Wait, I don't get a log. Wait, yes I do, I lied. I have constants. Fuck. Oh my god. It's fine. It's fine. I guess I could do... No, I would get 1 over constant. No, I wouldn't. I wouldn't. Oh, wait. Maybe I can cheese it. No, I would get it either way. Can I cheese it? Wait. No, I can't. I have to... change in potential energy, radius, and volume. So this is... the general form of this equation is... Let me find it. Written there. Sorry. It's buried away. It's, Wait, where's my... Come on. They always do this. They're always like, lol, we're not gonna give you the equation. I don't know why they're actually not giving me the continuity equation. That's not it. What? Why don't they give me the... They straight up just don't give me the general form of Navier-Stokes. It's, wait a second. Here you go. It's rho times dv, or total derivative, dt, equals negative gradient in pressure plus rho g plus mu del squared v, so the Laplacian. Yeah, so basically what this is saying is that, like, the change in linear momentum, so total derivative can either come from spatial acceleration, or it can come from, so like if you have a steady flow, but like as you move along the flow, the velocity is getting faster and faster, or it can come from like time acceleration, so like at a certain time. And then this is the pressure gradient, so that's like a force, and then this is the body forces, and these are surface forces due to shear. What is del? It's just gradient. It's kind of like a gradient. It's like an operator, so depending on how it's written, like del dot v has a certain meaning and v dot del has a different meaning, because it's not just a straight up gradient. You also don't, it's not like gradient of v. It's like it's a little weird notation, but yeah, it's basically just like linear momentum for Reynolds transport theorem, but oh god, operator, yeah. It's like the linear momentum for Reynolds transport, but just kind of like abstractified, and that's why you have all these partial derivatives because of the del, because like it turns out to be like cross and dot, like dot del and cross del, and I've used that in PChem 2 and thermo. Thermo, maybe? I mean, I think you might use Reynolds transport more. This is more about like... Just from my intuition, if I had to guess, because I haven't taken thermo, but also from people I know who I've talked to about taking thermo, like at least our thermo 1 is like it's all about like the internal energy function of like temperature and pressure and stuff, and talking about like ideal gases and that kind of stuff. And so tracking flows that are, you know, compressible, incompressible, whatever. Transport, I don't think I have a class called that, actually. We have, so I have to take fluids 1 and 2, and fluids 2 you need thermo for, and then we have to take thermo 1 and 2, and then we have to take heat transfer, and there's a systems dynamics or something. Alkaline engineers are 3 semesters of thermo. That's a lot of thermo. We have, I mean, to be fair, this is also a lot of thermo and fluids. I don't remember. There's another, I think there's one other heat class we have to take, but yeah. But I'm excited. I'm taking thermo 1. Phase? Phase? I don't, phase? What? oh, like phase shifts or something? Phases? Wait, let me... Phase equilibrium. Oh, I do not have to take that. Let me just see. I can pull it up, but I'm not about to actually pull it up. So I have to take thermo 1, thermo 2, fluid mechanics 1, fluid mechanics 2, heat transfer. I have to take vibrations and system dynamics. But I don't know, it's optional to take. I know there's classes on like compressible flows and stuff, but oh, that's a lot more in depth, because like we have to talk about, we deal kind of like, so for example, like this derivation even is like because we're trying to use it for pipe flow. So a lot of the stuff that we do is not really necessarily like, the most that I get nitty gritty is like the materials class I'm taking right now. And so like we have to talk about like all the different chemical like properties and like diffusion and, you know, a lot more very small stuff. But a lot of times it's more like, what's like the big picture, like how can we use this analysis for, like for control volume stuff. I don't know, we do like, what's a good control volume problem that like is a good example? Yeah, like this, like, you know, we might be using it, like arrows use it for lift and drag and stuff like that. And so you're interested in wakes that things are creating. Like that's why MEs would do computational fluid dynamics or this kind of Navier-Stokes stuff. It's just that there's a log, and I don't like that there's a log, and maybe I just need to plug stuff in before I integrate my stuff, but I think there's a shear. I think there's a shear too. I think I have to use the shear. I don't know though. Mu is viscosity, yeah. R over 2 plus C1 over R equals dV dz, or dVz dr, and then integrate these. You get dP dz times 1 over mu times r squared over 4 plus C1 ln r plus C2 equals Vz. I feel wrong. There are parts of it that I agree with, and then there are parts of it that I'm like, but, you know, actually, because if I say, so we know that when R equals R, Vz equals 0. And then we need another constant though. I think that's going to be the second condition we use, because that'll give us this, or r squared over 4 mu plus C1 ln big R plus C2 equals 0, but that's not really useful. Where did the r squared go? Oh, I divided by r. Brought that guy over. So it canceled one of these and it got picked up that guy. Let me look at what the shear equation is. Oh, I didn't even see it. No, that's so fine. There's a lot of stuff going on. And honestly, like, those are the kind of like mistakes that you just make when you do these problems. I also, like, I literally like did an entire thermo problem and I just forgot to write the thing that I was solving for in the problem. And I was skipping lines and I was like, oh my god. Such a silly mistake to make, but like, it happens sometimes. I think I need the shear. Have I done, we do fluid thermo stuff because like fluids is, you know, gas is a fluid, so there's some thermo, like we did Reynolds transport thermo. Oh yeah, our thermo is like data tables. I haven't actually done that thermo yet, but this is more like you have an aerosolized rocket fuel being pumped in and like a nozzle and that kind of stuff. So it's a little bit less, it's more like, here are the properties of this gas. And then V theta over R? I don't know if I have that. 1 over R. dVr over d theta. Well, okay, dVr is 0. Or VR equals 0. And then, I guess... But our V theta, I don't know about that. It's pretty easy. I have to do this exact thing next semester. Well, it's fun, I think. Or at least like my professor, because he gives us like, I mean, I think the best example of like why I actually sort of enjoy like my professor versus other ones is like, he gives us stuff like this problem where, so we have to do something called like dimensional analysis for MEs. It's kind of like if you want to figure out relationships between like a prototype you have in a model, you have to be able to understand like these things called dimensionless groups and how they relate to each other and how to make it so that you can actually scale up your properties if you're testing on a prototype. I have to do this next semester. No, it's over. And it's really cool because like you can actually, you see like a bunch of scattered data and you try and plot single variables against each other and nothing works, and then you plot dimensionless groups against each other and then that works and it's cool. Dimensionless numbers? Yeah. Like Mach number and Reynolds number. I think there's some in thermo as well. I mean, Mach you probably use in thermo. Bro. This one is really easy. Like, I'm gonna be real. This is just a process you do. And it like, you know, it's different than like the hard part of fluids. This is kind of just like, oh, we get to chill out and do some determinants and just put some matrices together and that's it. Did you have to take like a linear? I don't remember. I feel like this is not useful. This shear. Because I want the shear, but I don't want it in the theta direction, so I don't know. I haven't taken linear algebra, don't need it. It's gonna be real. Oh, linear is so important. I don't know how to say it other than that. Well, if you've taken multivariable, it's not as bad, I guess, but like, at least for MEs, like, we do so much work with matrices that it's impossible to avoid it. Anything where you're solving systems of equations, I think it's good to just take because it just makes your life like a million times easier. Man. They get theirs as 0 because they don't have a... Or they get their theta component. They use their theta component. Maybe I need to use one of my other components. Let's take a look in the garbage. What would be useful? I don't really like R, but maybe theta? No, I don't like theta. Everything is gone for theta. Maybe R, but there's no V. No, I used R, VR. Most everything is gone here except for this, and that doesn't really help me at all. I just plug everything into my TI-84, provided we can use one. I mean, if you know how to use matrices, then it's like, it's not too bad, I think. But if you don't, yeah, I would learn somehow. Okay, U is not a so Z is not a yeah. Well, I know Z is not a function of Z. Maybe I don't have a change in pressure over the Z. Maybe that's what it is. Would that fix anything? No, it also wouldn't be right because we have the change in pressure in the equation. And I don't know. I don't know what it could be. And to get like if you I've organic 2 and I haven't studied one bit, I'm not the same student I was anymore. I can't really afford to not study. It's like some of these things, most of the things, I don't know, my classes don't really ask for that much, ironically. I feel like if you do the work that they give you, then it's like you're gonna be fine. So that's just what I do. It's just that the work kind of takes a long time sometimes. And like if you want to actually get something out of it, you have to do it until you know it. Engineering classes are nuts. They are not that much harder than like, honestly, I've taken like, engineering classes are so much more straightforward than like some of the, weirdly enough, some of like the GEs that I've taken, because the general education classes, like if they're writing or something, like I don't know what they want and they're not good about like telling me what they want. Whereas like in engineering, it's like, I know exactly what they're asking me for in this problem. It's just, can I do it or not? Although I do like writing, but it's just frustrating sometimes. Man. Writing is so bad. It's bad for like a lot of STEM people. It's a common thing. I'm just gonna, can I integral? I don't know if I can even integral calculator this, I don't even know. Maybe I can just put it in Symbolab and Symbolab will love me forever and solve it for me. I'm just gonna have to use constants though. U over R. So we'll use X and then do the integral. But I don't know if I did, like, I don't know if I need to put bounds on it. I feel like it might be the bounds, but I don't know. It was nice catching up, yeah. Good luck with your stuff if you're not done, and then... Nice, Mike Demon. I'm not gonna put bounds. Wait, let me go over here. Wait, let me... If I'm gonna symbol lab it up, we're gonna put my shame out for the world to see. U over X. Mike blew up. It always blows up. No, it always blows up. It's always like the most inopportune time. Oh, you weren't here for the mic blowing up era. That just happens. Oh, I was gonna try putting a noise gate on, or not a noise gate, a compressor on. I don't have a compressor. It's awful. It's the worst. It doesn't happen on my other computer. A lol, funny. Okay, well, I'm glad it's funny and not like... I do have a compressor on. Oh no, it didn't fix it. Yeah, maybe if I put my attack time at 0, it'll catch it. I don't know. I scream really loudly, but then I would have to scream really loudly to test it, but I don't want to do that. Okay, U over X. U over X times U VD, oops. I have like too many variables for this to like even parse what's going on, I think is the issue. Like if this solves this, I'm gonna actually be so, yeah, illegal input. Input is not valid. Oh man, how do I mean, it might be time to, no, I can't. That's my Discord. I can't. I was gonna look it up. I can't. I haven't looked up a single problem for this class. I'm not starting now. Not happening. Ooh, tell me your secrets! I don't know, man. That r over r squared is so... When you multiply it out with the other thing, it'll just give you r squared over it. Oh. Wait. A second. Wait. Wait a second. It could be that this ends up being 0, and that this ends up being 0. Which means that this would be what we have. And then it would be r squared minus over 4 mu dp dz times, if this is like r, it was r squared minus, so this would be 1 minus, but then it would be 0. There has to be something that gives me that. It's gonna be like r. Wait, but we want the r. Oh, when we're integrating, we want to go from r to r. Not from 0 to r. Because that would be integrating, but we want a function. Ah, okay, so that's closer. So that's going to give us this. Which is the right thing. But that means these constants have to be 0. Which is a good question of how we can get C1. That's the only thing that's weird. Because I'm guessing, okay, if we get C1 to be 0, we have a pretty decent chance at getting C2 to be 0. But the thing is, like, C1 is gonna have to be, like... If we want to get the whole thing to be it, C1 is gonna have to be negative, like, ln over the first term. Get it to cancel out, and then C2 can be 0. Although C2 being 0, I don't think is a huge... No, C2 does have to be 0. What do I know about BZ? I know that it equals 0 at the top and bottom. And I don't know anything about it in the middle. There's also that negative, which is really interesting. But I guess maybe it's just going the other way. Like, I don't know which way their positive is, so that might not be great. It also could just be because they're doing... Wait, maybe... Wait, sorry, that's so dumb. Can you 5 minus... No, that should be positive, yeah. I feel like I always, like, goof that up. I always have to think about that, and I really shouldn't have to think about that. Maybe I should look... Let's maybe look up the, Let's look up, like, a different, rendition of the Navier-Stokes equation for, in cylindrical coordinates. I just want to see the most general one to see how other people write it. Okay, so this one sucks. Oh my god, this one sucks. Ugh, look at that. That's crazy gross. This one is more right, I think. So they also write it 1 over r. They pop out that r. That is fascinating, they pop out the r. Well, I guess they don't. Wait, they pop out the r in the other ones too. It's just, my book does it weird, where they leave the r in there. Wait, do they? Yeah, they leave the r inside the dr for the other ones. But this one doesn't. This one also pops it out here. Wait, this one pops it out here but doesn't pop it out here. And this one pops it out here and pops it out of all of them. I just need to see how to solve this part right here. Just that little part. It'd be r over mu, and then you just integrate it, but I guess maybe the other question is, where am I getting my second? Let me see where. So they get theirs from tau, I think, for the other one, which sort of makes sense because they're doing a rotatey boy. They're doing concentric cylinders, and they're also being asked to compare the shear stress. Whereas in the... Yeah, a lot of these are using their second condition as the shear stress. Wait, no, they aren't. They are. I lied. Oh, wait a second. Wait a second. They use this as their other condition. Wait, they use that as their other condition. Saying this is 0, so C1 is going to be this. Wait, yes. That's so close. Oh, we're so close. But we have that ln r still. Wait a second. Wait, you might be cooking something. Blop Bop. That's a really great song name. The locker song. Okay. Okay, wait a second. So we have this one. And we have this one. These are our two equations. So I guess we have to say shear stress is 0 at some point? Would that make sense? Is there a 0 shear stress? I mean, probably, because the shear stress has to start going in the other direction. So when little r equals 0, dvzdr equals 0. Is that what they're saying here? du dy at 0. In our case, it's dv dz dr. Yes. Because it's not being pulled back at all. That means C1 equals negative dp dz times r squared over 2 mu. Interesting. The plot thickens. There's a 2 in there. And then we say, for r equals r, vz equals 0. Which means we get... But it's the ln r thing that just like screws everything up. Like that just doesn't go away. We're just kind of stuck with that. Ugh. There's also like that 1/2 thing. Man. There's no 1/2s in there. Ah, maybe I'll email him about it. My professor. Yeah, I think I gotta do that. Oh my gosh, it's been 2 hours. I'm probably gonna wrap up soonish. I haven't really eaten anything and I kind of have class. Lol. Oh my gosh, I have my class that keeps canceling class. We have a final next week. In our class next week. And like, I don't even know what we're gonna learn in it. Or what we're gonna do in it. Well, yeah, I think I'm gonna call it early today. Man, this is really getting under my skin. I don't like not being able to solve something, or like not seeing why it works, or doesn't work. I think it's just a calculus problem, which is like frustrating. Calculus and boundary conditions problem, probably. The fact that I can't get it to work out. But it's just frustrating. I'll try and get an answer for you guys. I'm trying to think about Friday. I don't think I have anything Friday, really, so I'd like to stream. Oh, I have my midterm. Yeah, but that doesn't matter. So it won't be linear. Lol. It'll be, not linear. Although, I will try and do a speed run, I think, for parts of linear. It might be fun to do a really, really quick speed run for linear. Before the final. But yeah, I got time to do that. Because that's my last midterm, and then I'm just kind of hands off. I gotta do a lot of fluids. I gotta do more of this kind of stuff, because he's definitely gonna give us a differential analysis. He's gonna give us an easy differential analysis problem, probably. But I really see him doing a differential analysis problem, so. And this kind of stuff is really interesting, and I want to get good at it, so. Alright, I will see you guys later. Thanks for hanging out. I know a lot of it was just this one problem, but hey, we made progress. Sometimes engineering problems do just be like 4 hours long. Sorry. That's the pitfalls of streaming. But quarter's almost done, so I'm gonna be doing more. Gonna try and do fluids lectures. I have to write them, and I have to get some extra cool stuff prepared that I haven't get secrets. But yeah, I do wanna do some lectures, at least one. I think I need to think about it when I'm not like in the middle of everything right now, because my brain's like, oh my god, I can't do that. And I'm like, yeah, but we want to do that. And my brain's like, yeah, right. So, all right, I will see you guys Friday. Thanks for hanging out. Have a nice day. Bye.